Hello? 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 Earth to moon? Huh? Earth? Earth to moon? Hello? Hello? Hmm. Well, we're going to dismantle this music. And what you see before you is the Parkes Observatory in, I think it's Australia or somewhere, at night. No. Let's see if we can find. Wait. We're looking up some images here. Okay. Well, that doesn't help. That's what we're looking for. Alright, so let's see if we can make this work. Alright. So what you have before you here is a bunch of images. This one looks prettier. This is called the RF spectrum chart. And in order to get information that's understandable and that sort of thing in some form or fashion, we have to convert the radio signal into, say, an audio signal or a video signal to see what it looks like or hear what it looks like. Uh-oh. Uh-oh. So these are the different ranges. The bottom of each spectrum. And their associated usages. Let's see if there's a code thing down here somewhere. Let me just do that. I don't see anything. That's okay. So anyway, these are the different ranges. So you have VLF, very low frequency, 0 to 30 kilohertz. So that comprises the audio spectrum, like 100 hertz to 20 kilohertz. That's your audio frequency, that sort of thing. And then we have low frequency, which is 30 kilohertz to 300 kilohertz. If we do, let's see. If we look up ultrasonic frequency range, I don't know what that is. Here's This would be, like here it says ultrasonic is from 20 kilohertz to 2 megahertz. You've got animals, chemistry, medical, destructive diagnosis, some other stuff in there, bats. 20 hertz to 20 hertz to 20 kilohertz is audio frequency. 20 kilohertz to somewhere up in there is ultrasound, ultrasonic. Oh, there's some images. Let me see here. So we have audible sound, like for our hearing, is in this 20 hertz to 20 kilohertz range. Elephants can hear low frequency sounds. Bats can hear very high frequency sounds, like dogs and cats. Maybe they can hear sounds that we can't hear. It could be because their ears are smaller. That's a good analogy. Ultrasonic welding. Mosquitoes make, that's 1500 hertz, middle C. Upper ranging bats, 70 kilohertz. Blah, 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 blah. Interesting. Now, well, let's go back to the spectrum chart here. And while y'all looking at that, I'm going to open up a program called Paint. It's generally what I use to try to explain things in odd fashion. Now, it will take me a moment to, let's see, there's a window capture. Let's see. Let's grab MS Paint. Now I'm going to actually do, well, that's actually underneath the web page. And it should show up, though. Doesn't really want to show up. We'll just drop the web page for a moment here. And as you can see, I have a background image that covers my desktop, so important stuff doesn't get shown. So let's see, we'll grab that window. And we don't need to see the extraneous stuff there. And I will fill up as much as the window as I can, which it happens to fill the whole window. All right, so basically in a nutshell, and I'm not going to go over all of this. Well, I might go over some of it in sort of detail, but let's see if we take. Well, we need a graph, so we'll use. We could use. Well, I don't like to use white. Let's use this color. Actually, let's use. Yeah, that's good. And then let's see. We'll use large line. I don't really like to use lines. I'd rather just use a pencil. It's crooked, but it's supposed to be straight, you know. So if we imagine, we'll just put this arrow here like this. And this represents t, which is time. So time goes in this, well, it sort of goes from left to right. But when you have a waveform, let's say you have a waveform, this is like a sine wave type of thing, right? It's actually a damping sine wave, and then maybe it repeats itself. So the sine wave itself is actually going... Oh, my arrow is just crap. It's actually going in that direction. Or we are receiving, like as a person, we might have our ear, like can't relate to our ear, or like there's an ear there, sort of like an ear, you know, and then there's the eardrum thing. And so, like, we have sound that comes in, and sound actually, okay, the sound, for example, we're talking about is a frequency. Let's say that we're just looking at, this is actually multiple frequencies. There's harmonics in here because this is actually a sum of, maybe we've got a large frequency like this, and then we've got maybe we've got a medium frequency like this, and then we've got another smaller frequency like this, sort of. So these are all added together, and they kind of repeat each other. They kind of repeat. So that's what the signal looks like on what's called an oscilloscope. So an oscilloscope can take the electrons, add the electrons up, and make them into waves. I'm having a snack. So, we could say this is frequency is like cycles per second. How many of these cycles occur in 1 second? So a cycle begins here, and then it ends over here. So that would be however many cycles per second or whatever. And the oscilloscope has lines like this, and it can tell you, you know, exactly like what the voltage level is. In the real world, what we see is something like this. Sort of like this. Maybe they're bunched together. So each one of these peaks would represent this line, and the trough, which is this might be the trough here, and that would be represented by these guys down here. So this is the peak and this is the valley. And when you have different, it's a little bit more in depth, but if you have different types of frequencies that come in here, let's say you've got something else coming in here off to the side. Now you have what's called like where each one of these things cross right here. Those are called interference patterns, and they add or subtract to the waves and that sort of thing. If a person positions themselves in a null area, they won't hear anything. So the way that I study advanced physics is by waves. it's a little bit, it's quite a bit more difficult to study the amount or the number of electrons coming in or which way they're coming in or whatever. We'd have to have what's called a photoelectric device that will actually count the number of electrons coming in. I have to have another bite here. Whilst you all look at my marvelous artwork. So, our ears are such that it only picks up certain wavelengths. There's a formula that is, I believe, it's lambda equals 300, which is equivalent to C divided by the frequency. So this would be in meters. This would be in seconds. And the speed of light is in meters per second. So when you put meters per second in here, the seconds cancels out and what's left is meters. Now, in order to detect a frequency of a certain wavelength and to get information, okay, we want to get information. What's important to us is information. So let's go back to the website. And we're going to look up a term called the Nyquist theorem. Let's see, Nyquist theorem. Now, I find Wiki a pretty good source for basic information. Let's see, Nyquist frequency. So, the Nyquist frequency is the amount of data, like you want to be able to make sense of something. So, the Nyquist frequency has to be at least 2 times. So they're really equal because that would require oversampling, rare factor, blah, blah, blah. Let's see. If we can find well, they're not really going into it that much. Let's see. What if I look up, information, data, frequency. Well, some of this has to do with digital. So, in other words, you have to have a certain rate of data coming in order for the data to be intelligible. So, in other words, basically, I mean, I guess what we're trying to say is, let's see, let's go back to our illustrious design here. let's say that our frequency is 20 kilohertz. We're going to have, let's see here, let's bring this back up. I don't want this. Why can't they just give me a regular calculator here? Maybe it's Google Calculator. I don't freaking know. I don't want to find, I'm not dealing with Google anymore because it's just freaking crazy. Oh, this is bullshit here. Well, you know what? I'm going to have to go to Google. Because Google's giving me issues. So we're just going to have to deal with this capture. Alright, here's what I was looking for. Alright, so if we take a frequency of, let's say, 10 kilohertz, that's 10,000 hertz. We have to actually, the speed of light is roughly 300 meters per second. And the frequency is roughly 10,000 hertz, which is cycles per second. So the wavelength is going to be 0.03. Wait a minute, I might have done something wrong. So the way I do this, if I do a frequency of 4 megahertz. Wait a minute, that's not correct either. Yeah, 75 meters. That's the length, that's the half-wave length of a dipole. So, let's see. I'm going to munch on this thing here. When you see these numbers like PD8DX, those are actually amateur radio call signs, of which I seem to have one. So the frequency is going to be 4 megahertz. No, this one's not helping me either. Maybe this is 3.5. 3.75. Well, it's supposed to be a 75 meters. That's 76 meters. So what it does is it divides the number by 300, but I don't know. That's meters. See, if you have a 300 divided by the frequency in megahertz, which is 4, that gives you the total length of the dipole. So it's 37.5 meters on each side. Now, if I have a frequency of... So that's telling me I'm using the frequency, which is in megahertz. Because 300 is actually 300 million. Okay, so if we do 300 and divide it by 10 kilohertz in megahertz form, I believe that's... Look at the skull on... You can't see it, but there's a skull on the... Alright, so if I do... I want to convert kilohertz. Shit. 0.010. Oh, you know, we've got an issue here. Wait just a second. Sorry about that. We want web page. Assuming that's 10,000 kilohertz, all I have to do is multiply by 1,000. You know what? I don't know what I'm doing. I need to convert 10 kilohertz to the amount in megahertz. $10,000 hertz. Let's see. $10,000 hertz. One megahertz is... That's 1 megahertz right there. So if I divide it by, 1 megahertz, so what's 10,000 hertz in megahertz form? That's what I'm trying to figure out. 10,000, 100,000, oh, maybe it's times 100. Yeah, that's what I did. 0.010 times 1 million. Yeah. All right, so what we have is we've got 300 divided by 0.01, and that number is in wavelengths. That's actually in meters, huh? So it tells us that the antenna, if we were to make a dipole, has to be 30,000 meters long in order to receive that frequency. Now, it's impossible. The lower the lower the frequency that you go, the higher the length of the dipole has to be in order for you to pick that antenna up. So what we do is we make antennas that are different from dipoles to gather this data. That's the wavelength. It's like huge. So in other words, if I go back to let's see, if we go back to my illustrious diagram, maybe I can explain it. If we have, okay, if we've got this long waves coming in, these are like audio waves, okay? So if the wavelength is the distance between these bands. So when you have an antenna, now we'll go down a little bit lower. This is a dipole antenna. And the frequency that's coming in will change a different. When it arrives on the antenna and the antenna picks up the voltage, it probably looks like this. Maybe it looks like this. Okay, that's a full wavelength. Well, actually, no, that's a half wavelength, come to think of it. Because it's only picking up half the wave. That's why a dipole is it's a dipole, half wavelength antenna. You have vertical antennas that look like, I'm just going to put this over here. They have these bands on the bottom, these little things that stick out. And then we've got the long tower that comes up like this. And these antennas are generally quarter wavelength antennas. So instead of picking up half the wave, they pick up a quarter of the wave. So it looks like this. And then the rest of the wave is kind of disappeared somewhere, I think. But the point is the wavelength distance. So a dipole, this dipole here would have to be like 15,000 meters long to pick up a frequency of 10 kilohertz. We can't do that. So what it would look like, the wavelength is so huge that it takes so long for the data to come in. So instead, we make what's called a hydrophone, and it converts the lower frequencies into sound pressure. And I'm not going to go into all that detail about how that's done. And I was thinking of a way to make a hydrophone using a laser. See, I want to have. Well, I was thinking about making it extremely sensitive, So if this thing measures sound pressure and we build something that looks like this, if we build a cone or like a cylinder, I guess you could say. And we have a membrane that's across here. And the sound waves is coming in. Now the sound wave now is going to look like this. It's going to look, because it's so huge, it's going to come in looking like this. These are just flat waves and stuff. And they're going to cause this membrane to vibrate back and forth. And on the other side, the this is a sealed unit. I was thinking if I had a laser, in here, and this laser was emitting a light here, it'll bounce back. It'll bounce back and forth inside this unit, much like a laser itself. So when nothing's hitting the membrane, the voltage coming out of here is going to be 0. And then once these voltages change, what's going to happen is the laser is going to sense a difference. There'll be a pressure difference. But what's more important is there's actually going to be a physical distance. But I guess the only problem is because the membrane, these distances are going to be reflected across the whole membrane and not just one spot. Maybe it's possible to fill up the whole thing and put some kind of detecting thing on here to measure the distances. But anyway, so then it converts it to the regular sine wave. But hydrophones, there is a laser hydrophone they're just coming out with. And I don't know, I mean, for me, all I'm really thinking about doing is just listening to some of the high frequency ultrasonic. Let me go back to the website here. Get this thing popped up. If I can find the right one. So let me actually go here. So now if I just put down ultrasonic antenna, and we could do images. Now it talks about different things. Actually, what we want to look at is the antenna now becomes what's called a transducer. And generally, they're pretty expensive. So that's why we're thinking, it'd be nice to make one. Let's take a look at this picture here. What's this? So here we've got, there's a membrane, there's a mass, a bond. You got some electrode, you got some piezoelectric elements, and you got a compression bolt. Well, I don't know what that's all about. But it's basically measuring this, it's converting this distance. Oh, it looks like there might be a space there or something. And converting it to electricity. But I want to find, let's see, maybe we can look up simple membrane. Ultrasonic control. See, this is just a piezo element thing here. So it looks like what they did here. Well, wait just a second. How come there's no... Oh, you know why? Let's go back to all. Because we're in DuckDuckGo. Well, how come it doesn't show the web page? Wait just a second. Maybe I gotta go here. This item is no longer available. 1.7 megahertz. Looks like just they've got some material, and they've connected this material to, you can connect this to something else, and it produces a frequency and converts it to electricity. Probably it never worked to begin with. It's centered at 1.7 megahertz, which is kind of weird. It's some Japanese thing. Mechanical behavior of a circular membrane. AliExpress. High power, we don't need that. How to understand the simulation results of whatever that is. What's this here? Piezoelectric microphone. LDV. So this is a device. And as you can see, it's in micrometers. And there's different layering. And then it's showing the frequency range with a tuned circuit connected to it. From 200 to 500 kilohertz. So my interest range is lower, so I'm thinking this is not going to work for me. Let's see what else we got here. Immersion, ultrasonic transducers. We could even go to YouTube, actually, and see what's on there. 16-micron membrane. That's pretty slim. And then if you take your transducer and you want to put it deep in the water, it has to be protected so the pressure doesn't kill it. Maybe you've got to have something to equalize the pressure as it goes down in the water. Tell you what, let's just go to YouTube for kicks. YouTube always has all the answers, so let's see what they got here. We use ultrasonic membrane transducer. There's something, it's got some horn design. What else we got here? Now that looks pretty. Ultrasound probe extreme teardown. High frequency signal for ultrasonic transducer Arduino. I don't know who this dude is. Transducer array. Come on. Building a simple ultrasound cleaner. We don't want that. Stainless steel bowl. Those actually work too, by the way. Those are pretty cool. The learning circuit. How do ultrasonic distance sensors work? Basic ultrasound. Wonder what this is. Uh-oh, something's wrong with my stream. Oh my god, what's going on here? My stream's messed up, as usual. Well, that's obviously a musical. What is wrong with this? I'm trying to fix my stream, and I don't know what's wrong. I don't know how to fix it. Oh, what is going on? I can't fix this. Theater mode. Oh, this is weird. Huh. My stream is messed up somewhere. I can't figure out how to... What is wrong with this? It looks like I'm just looking at YouTube. I can't fix my stream. It shouldn't be doing what it's doing. I don't know what's going on. Oh, I can monitor it down here, but... Oh, there we go. It's working now. I have no idea what happened. There, is that... Okay, is it working? Finally. Huh. That's pretty strange. Let's go back here, because... That's not going to help. I tell you what, let's look up, we're not getting what I'm looking for. Ultrasonic, that one's $300. $7? Yeah, I don't believe that. I don't even know what that is. How can we find something here? The ping sonar, altimeter, and echo sounder. Okay, see, this guy's using an Idenu and one of those things for the phone. Robot sonar. Ha, if we build it, the fish will show up. Ultrasonic waterproof sensor experiments. I'm just looking for build your own underwater drone. Piezoelectric ring actuator transducer ultrasonic welding. I'm just not finding what I'm looking for. Let's see, underwater. Membrane. Sea bass underwater test Piezoelectric trainers for hydroacoustics. This one might be electroacoustics and transducer technology. Sonar working model. Transom mount. Marine acoustic transducers. Now they're getting into fish finders. That guy dumped his whole circuit down in the water. Well, this is not what I'm looking for. That's a whole hour's long. Let's take a look at this one here. Quick question. As a recent joiner and first-time viewer, what are you trying to accomplish? I want to design and build a hydrophone.
I'm working at the Acoustic Technology Group of Electrical Engineering. In the next few minutes, I'd like to give you
without having to spend hundreds and hundreds of dollars.
And transducers. So, electroacoustics is about recording, transmission, and reinforcement of sound. And here's a couple of examples. Recording of a voice, and that recording could be played back either in your living room or over a mobile device. Interaction, current in a wire that moves in a magnetic field is creating. And the other one is the electrostatic, which is basically having a charged capacitor and then allowing one of the high frequencies a bit more, creating a brighter and perhaps.
This guy's just talking about.
The microphone that's important is the directivity. So how sensitive is the microphone to sound?
Not going to help. There's different materials that you can use to make membranes for hydrophones. I watched these videos on this some years ago, and I can't seem to find anything. Because everything's, they're talking about piezoelectric to convert the stuff, the sound. But
in hydroacoustics, piezo elements are used, for example, in sonar applications, as part of locator beacons, and for underwater communication over several kilometers.
Well, that's just really not going to help.
Hydroacoustics covers several underwater applications, from object recognition to signaling. For these purposes, the longer the distance that has to be covered...
Oh my good lord, everything's so slow today. Yeah, I wanna build a hydrophone to talk to the fish. Just an ultrasonic transducer. I'm gonna build the amplifier stages and all that stuff. Just to listen to the fish.
Let's take a look to the overview for my today's talk. So at the beginning, I would step in our topic of in vitro diagnostics.
This is for
and
liquid
give some
handling.
Information about the current challenges in the field of.
My internet is slow. I just found a virus on my computer and
the
spent all night trying to
media,
fix
in
that.
this case, air. So there, all the mechanical energy of the ultrasonic waves are concentrated, and this leads to the ejection of a droplet out of the liquid reservoir. So as I said again, this is also a very dynamic method, and it's completely contactless and avoids any cross-contamination. Which piezo elements can be used for such a technique? In the center of the slide, you see a scheme of a curved piezo element called focus bone, or it's also possible to use other kinds of focus.
Well, this is a little bit not really what I want to get into here.
And of course, the manufacturing, as well as the manufacturing.
Yeah, I don't know what they're talking about. Well, we're going to have to look at this, I think. This isn't what I'm looking for.
I have just wired up an underwater transducer, which is a lot like the HCSR04 depth sensor. These are just the words I use now. So you may be familiar with the depth sensor HCSR04,
Nope.
sonar echolocation sensor in the lake.
It's just giving me false readings.
Yeah, that's not what we're looking for. Let's try this other link here.
I know that the water's getting deeper because I'm getting lower in the water. Okay.
Why is this so slow today, I swear? The alias you set this command to be of commercial does not exist. Oh, that's my Nightbot trying to tell me what to do. Hmm.
Of course, and also I moved, so I had to redo my whole setup here. Now, also, if you notice, there's only one of these, when on the old board there's two. It's because they're all integrated inside this waterproof case that I didn't test. I don't know if it's really waterproof. But
These look
I
like
would
the old
guess that
phone
it's fairly
transducers.
safe to put it out in the rain without dunking it in water. So
And this is not
also, it comes with a
looking
2.5
for.
meter cord attached to the sensor, so you can really locate this guy far away from your project. So
All right, we're gonna look up something else here. I saw some pictures of this thing, but I don't know if this is gonna work here. I wanted to talk about membranes for, what's this? That looks somewhat interesting. This guy's using, well, see, speakers they only go so far in frequency. Ultrasonic sensor. They're not really called sensors. They're called
Ultrasonic sensors are a cost-effective and reliable way to both detect object presence and measure distance to objects. They fit this sweet spot between proximity sensors, which are inexpensive but limited to a couple inches, and laser distance sensors, which cover a huge range but cost more. Ultrasonics fit right between these two and cover ranges up to 3.5 meters. Ultrasonic sensors work in environments with smoke, dust, fog, and steam, things that can be
3.5
difficult for
meters. This is
optical
not
sensors and
what I'm
laser
looking
distance
for.
sensors. This makes them ideal for applications like when you have items coming down a conveyor that are different. In a separate set of videos,
Right. I don't know. Let me look at this again. Hydrophone. Membrane. Material. How to build a hydrophone. Do-it-yourself hydrophone. I think we're getting warmer here. Oh, this guy drew lines like I did. Whiteboard hydrophone arrays. Different types of pressure tanks. Getting started with a fiber optic hydrophone. Mm-hmm. Seven eerie sounds recorded in the deep ocean. Yeah, that's kind of what I'm interested. 0 to 50 hertz. This guy's, oh, this might be interesting. He's looking at frequencies below the sound of audio hearing. I don't know what that video is about. Well, there's an ad. We don't really need to listen to that. Let's go up. Wait a minute. I just clicked on that. Let's look at this one. Wow, this is really slow. It's just annoying. Skip ads. Well, it doesn't say. Music. Check out this album. Well, those are frequencies below 50 hertz. And I don't know what's going on here. My web page is not cooperating.
Hello, this video tutorial is about hydrophone selection for your sonar point recorders. Now, sonar point is a very flexible system, and one of the degrees of freedom that you have is that you can swap out the hydrophone. How to do that is fairly straightforward. You open up, as you have seen in a previous video, the recorder. We recommend first on the electronic side. I only have one screw in here. Take that out. And now I can open up the recorder. As I pull out the electronics end cap, you will already see there's a connector here at this end, and that mates to your hydrophone assembly. The hydrophone now sits on the other side of the recorder. Again, you remove all the screws once more. I only have one screw in here.
So they're connecting the recorder amplifier stuff right into the unit. And then sending the data up through the cable.
Take it out and remove the end cap. And here you go. So you have several options of hydrophones available to you, and they break fundamentally into two categories. One is the end cap integrated type, of which you see two here. This one is for operation up to 33 kilohertz. It's called the SH33. This one for operation of up to 125 kilohertz, called the SH125. And they are very rugged devices. You will not easily damage them. And they are also programmable. Their sensitivity, their frequency response is programmable through solder jumpers that you see here on the inside.
Huh.
The other option is cable connected hydrophones, also sometimes called free field hydrophones. They go through a connector like this. You can order that with your sonar point recorder or order it as an additional device. And your cabled hydrophone plugs into this connector, and now you can have a hydrophone that is arranged in a way that you want it and fully
You could just use a
surrounded by
tin can.
water in all directions, which will give you the highest fidelity.
From
So
there,
these are your
just
two
like need a
general
MIDI cable
options.
jack.
And with that, we will look a little bit into the pros and cons of either hydrophone configuration.
All right, let's first look in some more details at cables
I want sensitivity.
or free field hydrophones. And we can see
Like,
a use example here.
for long
There's 4
distances and
recorders
stuff.
mounted on this frame that will sit on the seafloor. And each one of the 4 recorders is cabled to a hydrophone array, hydrophone forming an array, ultra short baseline array, as you can see here, that we also discussed in some of the earlier tutorials.
Ultra short
So that's one of the
baseline
advantages, the mounting
array.
flexibility that you have. However, you also have to be careful. The hydrophones, most of the cabled hydrophones are not very rugged, so you want to have reasonable protection for them so they will survive the deployment. Now, one significant advantage of having a cabled hydrophone is that it's surrounded on all sides by water, and that is called a free field hydrophone. And you can see how that behaves really as compared to an air-filled one. Here, this is one of our earlier recorders, a Micro Mars, or an oil-filled one. This is a sound trap here. By seeing how it reacts to a sharp pulse, a so-called impulse response. And here you see how this sharp pulse is perceived by a free field hydrophone. And now look at what we see here on the oil-filled device, and you can see some reverberations going on here. It says mean duration 115 microseconds. And then here, Micro Mars, an air-filled device, has the highest amount of reverberations.
You'd be surprised how sensitive something like that can be.
This has some impact if you are, for example, have an automated classifier looking for echolocation clicks of a certain
I'm just starting to learn about it. I figured I'd stream about it because
having the reverberations might confuse
I'm into electronics and all that stuff, so I said, what the heck.
Now, another result of that is that depending on the frequency of the signal here in a device, in an air-filled device or a hydrophone that's mounted on an end cap, you will get some frequencies where you have elevated gain, followed by other ones where you have a lower gain based on whether the interference between the
that's cool. Thanks
direct signal and the reverberation.
Yeah, I'm gonna look into the piezoelectric elements. I mean,
you see that here for a bottlenose dolphin click
that's
spectra,
what seems to be the general idea of how to go.
A free field hydrophone on a subarray. You see a fairly smooth progression with frequency. And here we have Micro Mars end cap mounted, and you see these peaks and valleys in the spectrum, and they are probably, I would argue, due to the reverberation. So one significant advantage of cabled hydrophones is that you have that very clean, free field response, so a very high fidelity reproduction of the sound. Another thing is that when you mount a hydrophone on the end cap of an instrument, it's quite close to the electronics, and so you can have some noise, a recorder self-noise getting into the system, and you can see that here. This is on a sonar point, and here at 22 kilohertz, here we see these little clicks here in the spectrum. And that is actually as
that's not me talking, by the way. I'm just trying to get some information about learning about hydrophone design and that sort of thing.
Noise here. With the cabled hydrophone, you don't get that, and the reason is simply that it's far away from the electronics, and it's surrounded by seawater, which has a shielding effect. What free field cabled hydrophones do we have available right now? Right now we provide or support the hydrophones that are manufactured by HDI, and you would buy them through Desert Star. They are connected to our specifications.
2 hertz to 30
their preamp is programmed to our specification. You do get a calibration sheet that gives you the sensitivity for
So I'll
each
bet those babies are a
individual
little
unit
bit
that you
expensive.
receive. These are the serial numbers here. So they're individually calibrated, although they are only calibrated in a low frequency range, I believe, from
I wonder how
a
much
few
them
hundred
are.
hertz to a few kilohertz
They don't
is
look like
where
they're very strong,
HDI
though.
calibrates them in. Now moving on to the end cap integrated hydrophones. On your sonar point device, here you see a sonar point recorder, and the hydrophone is here where I'm pointing to right now. This is an acoustic release it's connected to, and you can see that the mounting is very simple here, and the hydrophone is very rugged. It can take some banging around, as you've seen in the video segment earlier. Here you see it underwater. This again is the recorder. This is the acoustic release. There's a sacrificial weight down here. And this one here is actually the SPP 1000 synchronization pinger in the subsurface float. So the ease of mounting and the ruggedness is certainly an advantage. And the other advantage is that for our hydrophones, be that the MH33 here, which is for use up to 33 kilohertz, or the MH125 for use up to 125 kilohertz, you can program the frequency response and sensitivity. Clipping will occur, and this is computed based on the characteristics of the preamp and the hydrophone. The range.
I wanted to get something a little bit more, get into something a little bit more simple, but
Back to that.
this
So
is probably out of my.
Therefore, the recommended uses is just if you have extended and tough deployments, where your instrument.
What's going on there? Let's see. Well, there's a do-it-yourself hydrophone. Let's check this one out here. Yeah, see, he's piezoelectric. That's the things that come off the phones. They used to make them from the phones. I'm not using those. Oh, I see what he's doing. Well, wait just a second here. What about the transducers, though? Oh, he's got a crimper right on the back of that thing. Good old electric tape. Oh, he's holding the thing. What's he holding it with his mouth? Now, see, that's not a good idea. What the hell? What the? Oh my God, that's just terrible, because that's just going to dampen the signal for one thing, and to have that thick-ass wire in the middle, that's just going to dampen the transducer like crazy. Yeah, I want to see this bad boy in action after he gets done. What about this other stuff here? Wait, hold for it. Plastifilm? Alright, he's dipping the whole thing in that so it doesn't leak. What did he do with the, Oh, we just hold the fort here because he had these guys over here. What did he do with these? Unless he took... Yeah, I don't know what he did. It looks like he just took a thin copper strip. Yeah, I don't think so. It's not saying what they're doing with those other transducers that were sitting there. He just cut some rings up. Oh. These were ones that he had already made. That's what these are. They're not those phone transducers. I think I came to this website once. Yeah. Not what I was looking for. Let's see what this one is. You don't want to use metal. You want to use... You have to use a membrane, and like the membrane's really thin. And then you have to seal it, and it has to be able to take the pressure underwater and everything else. I'm going to check something. I've been having a problem with my computer. And it almost acts like it's acting up again. Oh my god, look at the Google Chrome shit in here again. What the holy hell is going on? Look at all of this. I'm not using... Am I on Chrome? That's Firefox. I may have to delete Chrome or something. I don't know what the hell is going on. Look at all this Google Chrome crap in here. I'm not even using this. I'm looking for... Now that's giving me an issue. Oh my god. What's going on here? OBS. OBS has this way of adding extra browsers or something. That's not supposed to be happening. Unless, if it's because I got the windows open. And I probably just closed them. It's still sitting at freaking almost 60 degrees. I don't know.
Education excellence. Technology and engineering for knowledge, or Cozy Tech. While the cord grip secures the cable as it enters the container and provides strain relief at this point of entry. Now, for jacket. Suitable connection is made. Now, following the technique used in the previous step, match the black wire from the microphone to the shield wires from the hydrophone cable.
I don't like this. There's just something wrong about this design.
This bumper ultimately provides an airspace in the final pot of the assembly in which the piezo microphone element can vibrate. Now this completes the preparation of the microphone element. We can now gently pull the hydrophone cable back through the nylon cord grip until our tape connections touch the bottom of the PVC bushing.
He taped those. Did he even solder them? Looks like a
Then,
piece of
holding
PVC.
the PVC bushing in one hand, we'll tighten the compression nut with the strain relief against the nylon body of the liquid tight cord grip.
This is sort of what I was looking for. And it looks like I may be stuck with having to use a PVC
When fully
connector.
tightened, very little space should be
But
between
this is-
the two components of the cord grip, and hydrophone cable should be held securely in place. Now, before we continue any further, it's now a perfect time to test the electrical connections and the general function of a microphone element. So for this test, we're going to need our audio amplifier and parts from the hydrophone assembly we've just created. First, though, we need to use a Phillips head screwdriver and remove the back battery cover of the audio amplifier. We're doing this so we can connect the 9-volt battery to the power connector housed within.
Those look like them little speakers that you get when you talk back and forth across the room.
Now we're
replace and secure the battery cover with the original screw.
Why did he have to go over putting a battery in there? I mean, honestly. We're talking about a hydrophone, not hooking up a battery to an amplifier.
Once that's done, we're going to plug the 3.5 millimeter male connector of the hydrophone cable into the input jack, which is the top jack of the audio amplifier. And we're going to turn the amplifier on to full power. Now, if the electrical connections have been made appropriately, tapping the piezo element will emit an audible sound from the audio amplifier or speaker. There you go. Now, this simple test will ensure that the microphone element is wired properly and is operational prior to
Where do these
potting the
people come
components
from?
within the two-part epoxy adhesive. If no sound is heard by tapping the microphone element, you need to ensure that the amplifier is powered, the hydrophone is plugged into the input jack,
This
and
is,
check
I hate
all
to say
wire
this, but this is
connections.
really sad.
Now, once the microphone connections are tested successfully, we can move on to the final step of potting the microphone element within the hydrophone container. The use of a bench vise or other suitable tool is recommended to assist in supporting the hydrophone container upright and level when injecting the two-part epoxy adhesive. If no such tool is available, a cardboard box can be used as a simple alternative. Let's clear away some of these tools that we don't need right now.
What the heck is he
And
doing?
move our hydrophone container over. So as an example, you can use scissors to cut a slit inward from one side of the cardboard box, followed by creating a small hole about 1 inch in diameter at the end of your cut. Now, it doesn't have to be pretty.
It ain't gonna be pretty either. What the? What is this guy doing? I don't feel so bad now. I'm telling you after watching this. I don't know what the hell he's doing. Nice circle.
Now, this is going to provide a means to securely hold the assembly in an upright position, allowing the epoxy to be injected directly into the
Why didn't he
PVC
just
bushing
use a
of the
pair of
cardboard.
vice grips? I mean,
Now we're going to insert the hydrophone container into the hole of the cardboard box with its open end facing upward until it bottoms
you know, most people
out
don't have
within the
cardboard
top of the
boxes.
box.
I'm sorry, but
The slit allows you to insert the cable,
all of mine are full of stuff.
and there you have it.
Okay, that's nice. Now what?
Now put on your rubber gloves to protect your hands prior to working with the two-part epoxy adhesive.
This is so not going to work. He probably doesn't even have a test at the end. This is very sad. What did he do? He filled the whole thing? What?
Next, we're going to gently bend the wires to the microphone element over and position the element bumper side down against the surface of the epoxy until it's parallel with the top of the PVC bushing.
Oh my God.
Depending on the speed with which you injected the epoxy, you should have a few minutes to maneuver and position the element to ensure it's centered and level with the surface of the PVC bushing. A paper clip is a perfect tool to assist with this process.
Oh my God. You gotta be kidding me. Look at the epoxy coming up over the top. Why did I even watch this
Now, once
video?
you feel
Let's try something else here. I'm sorry, but that was just really sad. All right, let me try, let's just see what this crap's all about. Let's see if I can find something. Waterproof pizza mic. Ooh, what's this?
Forms and survey.
Well, if we have to watch it, that's fine, but we don't have to listen to it.
Hello everyone. In underwater climate monitoring. According to National Geographic, in 30 years, coral reef could be gone due to the bleaching. It is extremely important to monitor them now because they are. But the problem, however, with this approach is generating acoustic signal consumes a lot of power. And if the sensor has a battery, it will drain the battery very fast. And what you need to do is to go out, replace the battery, and come back. But unfortunately, this is very costly. In fact, a research vessel costs around $50,000 a day to operate. And this approach becomes very costly. In this talk, I will tell you how we can get the best of both forward and we can design a system that can give us ultra low power and cost efficient communication while having a sufficient throughput. Let me give you an example. You can think of it as a guitar and be multiplied by a 10 to 100. Also, it leads to a very bulky solution. And importantly, the area of these piezo's will generate unwanted directionality, and we may focus the reflection to a specific point, and we may not be able to communicate a new form of vibration and resonance. Those individual piezo's will be design such metamaterial structure and how we evaluate it that leads to boosting our throughput and range. The key idea was to create a coupling between only two piezo's, and with this coupling we were able to synthesize many more resonances. Let me explain to you what I mean by this. So what we did was we took one piezo, which is shown in yellow, with a resonance frequency at 20 kHz, and we took another one shown in blue with a resonance frequency at 40 kHz. And we placed the smaller piezo inside the larger one. Then we filled the spacing between two piezo using polymer, which is a soft material. Now if we take a look at the vibration profile of the structure, what's interesting is because polymer is very soft compared to the piezo, the resonance of each of those individual piezo's will be reflected in the vibration of the entire structure. So if you take a look at the amplitude of the vibration for this structure, we will see the one resonance corresponding to the first piezo and another resonance corresponding to the second piezo. But now, because we defined a polymer between those two piezo's, which creates a constraint on the movement of those piezo, this constraint leads to generation of new form of vibration and resonances that fill the gaps between these two main resonances. And as a result, we can get a structure with a wideband vibration. Now, let me explain to you visually what is happening in this structure, which can give us a wideband resonance. So if I take one frequency like this one, which is closer to the resonance of the first piezo at 20 kHz, this is how the structure would look like at this frequency. The heat map I'm using here, red indicates the high intensity vibration and blue indicates low intensity vibration. In this mode of resonance, we can see that the outer piezo is vibrating strongly while the inner one does not have a strong vibration. Now instead, if I take another frequency more closer to the resonance of the second piezo, we will get this one, which you can see the inner piezo is now vibrating very strong and outer piezo does not have that level of strong vibration. Now instead of taking these two extreme, if I take a frequency in between, we will get a completely different mode of the vibration, which is generated due to the coupling between the vibration of these piezo's. In this mode, for instance, the edge of both of these piezo's are vibrating at a frequency of 20 kHz. Inner piezo has the resonance of around 40. Using ultra-wideband node, we can do out-of backscatter, and then we can filter direct path signal that enable U2B to extend the communication. Now, let me tell you how we implement and fabricate our prototype. To fabricate our structure, as I mentioned earlier, our node is composed of 3 layers. We have one piezo in the outside with the center frequency of 20 kHz. Inner piezo has the resonance of around 40 kHz, and we built this 2 piezo ceramic transducer from stem. And for polymer, we use 2-part polymer solution from BJB Enterprise, and we mix it and we create it inside the lab. After this, we 3D printed 2 caps for the structure, and we laser cut washers on top of these caps. And we assembled the whole structure using a screw and nut and tighten it. Eventually, we encapsulated the whole structure with a polyurethane polymer, and we let it to be cured overnight under a high pressure inside the pressure chamber, and that's the finalized U2B node that we were able to fabricate. For our evaluation, we performed our experiment in the charged river in different weather conditions, such as snow and rain, and also we used Hydrophone resin TC4014 to receive the signal, and this hydrophone was connected to the USRP software radio, and at the end we demodulate the signal and decode this FM0 in MATLAB. In total, we ran over 400 experimental trials at different range, throughput, and number of the node. Now, I want to just present you 2 of our main results. And for the rest of the result, I would like to invite you to read the paper. The first result is about throughput. The experiment we did here was we changed the backscatter rate and we tried to decode the signal. So here what I'm going to show you here is on x-axis I do have the backscatter bit rate, and on y-axis I'm showing signal to noise ratio. For underwater communication, the threshold usually is defined as a bit error rate of 10 to the power of -2. So I'm going to use this threshold to evaluate my throughput. Now, let's first take a look at how our period system will perform. In this system, you can see that the SNR goes lower than the threshold that we have, as low as about 4 kilobits per second. And if you're lucky, you may get something at 5. But generally, with this design, the throughput is limited in the range of 3 to 5 kilobits per second. But now, using this, the U2B design, if we test its throughput, this is what we'll get. So we can see that the SNR of U2B remains well above the threshold up to about 20 kilobits per second. That can enable us to do many more applications, such as streaming image or even low quality videos. Now, the conclusion here is with U2B, and due to its ultra wideband nature, we were able to boost throughput by about 5 times over the state-of-the-art system. Now I will show you how we were able to extend the range. The experiment we performed was we changed the distance between the backscatter node and the co-located transmitter and hydrophone. What I'm going to show you is on x-axis I'm showing the distance in meter, and on y-axis I'm having signal to noise ratio.
That's like 60
I want to remind
90
that
feet,
with
100
our
feet.
period design, we were able to only achieve up to about 10 meters of communication. Now, with U2B, this is the SNR that we'll get over distances. And now you can see that with this new design, And by performing out-of-band backscatter, we were able to significantly...
That was interesting. Let me look up something here. Let's look up something here. How far can a transmit sonar? $25 to $100. What? Will start producing foraging decals once a mid-frequency sonar is activated, even though the sonar frequencies far exceed sound production range. What's this? A phased array sonar. Oh, this is interesting. The songs follow a distinct structure. Base units of a whale song, sometimes loosely called notes, are single uninterrupted emissions of sound. The sounds vary in frequency. The units may be frequency modulated. The pitch of the sound may go up and down or stay at the same note, amplitude modulated. However, the adjustment of the bandwidth on a spectrogram representation of the song reveals the essentially pulsed nature of the FM sounds. Killer whales have been observed to produce long-range calls that are stereotyped in high-frequency traveling distances, 10 to 16 kilometers. Their missiles conducted using military data showing that whale noises travel for thousands of kilometers. Research by Dr. Christopher Clark of Cornell conducted using military data showed that whale noises travel for thousands of kilometers. Holy shit. Adjust their song to compensate for background noise pollution. Moreover, there's evidence that blue whales stop producing foraging decals once a mid-frequency sonar is activated. Huh. Prior to the introduction of human noise production, Clark says the noises may have traveled right from one side of the ocean to the other. Blaming large-scale shipping. Ambient noise from boats is doubling with each decade. Bioacoustics. Underwater acoustics. Who is this fella here? Researchers use hydrophones. Maybe this is all in the wiki. Yeah, maybe I should go here. Where is this guy? The frequency modulation aspect of the sounds is interesting. Dr. Christopher Clark of Cornell. What's this? Cornell. Ship noise. Noise can be burst pulse type, produced by propeller cavitation, etc. Low frequencies may be generated by engines, higher frequencies by rotating gears. Up to 2 kilohertz. Large traditional ships have dominant tones with source spectrum levels near 180 dB. Consequences of masking may be serious, particularly in the case of long-range communication. In a simple 20 times log range transmission loss scenario, an ideal type of situation in which sound energy spreads out spherically, any 6 dB increase in background noise level reduces the communication distance, the range at which the signal can be heard, by a factor of 2. But when propagation approaches cylindrical spreading and transmission, the loss is close to 10 times the log of the range. The same 6 dB noise increase reduces the communication by a factor of 4, and the area by a factor of 16. This is cute. 3 different man-made noises recording in the Ligurian Sea. Impulse noises below 1 kilohertz from a jackhammer used for construction 40 kilometers away. That's what we're talking about right there. God, think about all those fishing vessels that were out there doing all of that. Do you realize the destruction that they're causing to the noise in the ocean with all those ships? That was interesting. What do we got here? A lot of stuff. That seems to be gone. Most hydrophones are based on a piezoelectric transducer. Blah, 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 blah. One phase was a 1 millimeter in thick brass diagram coupled by a short brass rod to a carbon microphone. High acoustic impedance of piezoelectric materials. temperature synthesis. Sound propagation. Sound travels more slowly in fresh water than in seawater, though the difference is small. The speed of sound in feet per second is thus, so if the temperature goes down, it's going to be slower. If the depth goes up, the speed will be quicker. Ocean temperature varies with depth, but between 30 and 100 meters, there is often a marked change called the thermocline, dividing the warmer surface water from the cold, still waters that make up the rest of the ocean. 30 to 100 meters, that's like 300 feet. This can frustrate sonar because sound originating from one side of the thermocline tends to be bent or refracted through the thermocline and may present in shallow coastal waters. However, wave action will often mix the water column and eliminate the thermocline. Torpedo. Strandings of fish have been shown to be highly sensitive to mid-frequency active sonar. Other marine mammals, such as the blue whale, also flee away from the source of the sonar. Those are signals that are transmitted. To achieve regional directionality, frequencies 1 kilohertz and below generally require a large size, usually achieved towed array. Low frequency sonars that are loosely defined as 1 to 5 kilohertz or 5 to 7, also low frequency. Medium frequency is defined as 5 to 15. Their domes had size approximately a 60-foot personal boat. Holy fuck. For lower frequencies, linear towed arrays have therefore been used. 30-inch quartz projector worked at 9 kilohertz. So 17 kilohertz. Yeah, we're talking thousands of watts here to produce the sonar to detect. We're not interested in that. "100 kilohertz gives medium resolution, 500 to 1,000 meters. 300 kilohertz. So the higher frequency, the lower the range. Longer range sonars, etc., etc., etc. Okay, that's interesting. I don't know what this is. That has to do with using sonar for acoustical oceanography. That's what I was looking at. Hearing range of marine mammals. That's interesting. Marine mammals and sonar. Acoustic signature. Noise map. Remote operated vehicles. Live hydrophone streams from killer whale habitat. Hydrophone introduction. Passive acoustic monitoring. Build your own hydrophone. High quality hydrophone. I think we're making some progress here. What's this? 29 captures. Deposits.org science measuring. Where's this at? April of 2006. Piezoelectric material. Yeah, but I wanted to build something that, how to build a hydrophone. How sound is used to study mammal distribution, navigate, temperature, to text-based map. I don't know what this is. Web.archive. That site's probably not there. However, this site is here. Oops, wait a minute. Oh, that looks like a good site there. Now what's this? Another web archive thing. What are they talking about? Cavitation. Cavitation anyone. I don't know what that's all about. Do you hear? Fill in the blank. Hydrophone activity. Hydrophone instruction. Oh, this is a class or something. PamGuard software. What is this? What is this? PamGuard. This. This looks free. I wonder what this is. About PamGuard. This isn't pulse amplitude modulated decoding, is it? Doesn't really say that much. Core features. Maps, utilities, sensors, detectors, sound processing. PAMguard plugin modules. AIS processing. Holy shit. This is like everything. Huh. Marine mammal hearing. Huh. I'm not sure exactly what that's all about. Let's see, Acrobat. Hydrophone construction. Preamp design. This is coming from this website. Oh, this is not good. A cheap, sensitive hydrophone for monitoring. Pizza ceramic. A brass disc. The disc is supposed to be like ultra thin. Huh. O-ring spacer. Where's the... coax cable. Okay, so this should actually go back to some sort of a preamp. There should be a preamp connected. This coax design. Like if you put a preamp in there. Nylon screws. O-ring. It's an O-ring. That's going to dampen the signal. Polycarbonate. To hear underwater signals on headphones, you need at least 40 dB of gain and a simple preamp to provide this. In air, this will function as a poor quality microphone, but underwater, the sensitivity will surprise you. If you have access to it's about 5 kilohertz, etc. Is there specs on this thing? Well, this looks like something. The frequency response is fine for listening purposes, but is not flat enough for analysis. Buy a professional ball hydrophone if you plan more serious studies. A ball hydrophone. That's interesting. We could save that. This page cannot be reached. Paste, downloads. Well, that page cannot be reached. Precision Acoustics, leading global manufacturer in hydrophones. Products, power measurement, acoustic materials, piezoelectric materials. Now this is what I was looking for. Unpoled PVDF film. PVD student starter kit. Let's see. What else have we got in here? Guess I only ended up with that website. I'm asleep. Underwater acoustics. 10 hertz and 1 megahertz. I wonder who's measuring me. Well, this looks interesting. That has an air cavity. Listen for whales, listen live. Current orca sound hydrophone locations. Where the heck is this? Victoria, Ports Townsend. live.orcasound.net. I hear something interesting. I heard a little click there. Oh, that has a lot of hum in the signal. They could have done a lot. They could have done a lot better with making that. Oh, that's probably a boat. You're hearing a boat right there. It's cutting into the noise. We heard one little. Let's see what this is. Oh, that's like, wow, that's like really high pitched. Page not found, of course not. Let's go to Amazon.com and we're gonna type in ball hydrophone. Oh, there's a kit there. Ball hydrophone kit. And of course, we always go by priced high to low. Why are we looking at recorders? Let's look at, there was a kit though. Let's see what this brings up. Keeps bringing up recorders. Let's go to, let's see here. Ball hydrophone sale. $100 on Etsy. $20 to 200 kilohertz. Hydrophone with preamp. $10 to 100. Spherical hydrophones. What's some in a different country? Home Depot. Yeah, go to Home Depot. It's where you get. You know, I could have told you that toy. What, 2.5 hours ago? I could have told you just go to Home Depot to get your hydrophone. You know what I mean? Pizza high density spheres for hydrophone from China. These Chinese people have everything. Piezoelectric ceramic. Piezo ceramic discs and cylinders. Piezo ceramic. Nice web page. Wow, let's see. Let's look up piezo ceramic transducer. Ooh, here we go. That's on eBay for $10. I wonder if that's on Amazon. Now we're talking, see? Now we're talking. See, you gotta do the research. You gotta do the research. And eventually, you'll find something that's interesting. Here's 5 for $10. Only one left in placed in no order. Acoustic pickup guitar stuff. Piezoelectric disc elements. Piezoelectric soft pickup. Piezo ceramic disc wafer plate for a buzzer. Ceramic trigger, buzzer, drum, guitar. .41 millimeters. .25 millimeters. 27. So the best kind to get would be, well, I don't know. Those are 10 millimeter. So that would be for higher frequencies, wouldn't it? You'd think. Why don't they show a range? Three to 5 kilohertz. Resonant impedance is 300 ohms. .27 ceramic right here. 20 pieces. Let's see what this is. Ratings. UX cell. UX cell. UX cell. uxcell.com. Reliable shop for MP3 players. UXcell Pizzo. They got a shop. Let's see. How to determine frequency of piezo diameter. Oh, I spelled that wrong. Piezo calculator. Determining resonant frequency. Resonant frequency. Disk. Choose material. I don't have one. Millimeters. Outer diameter 20. .106 kilohertz. Perform another calculation. Cylinder. Radial. Millimeter. 10. I don't know. 2 megahertz. Huh. Okay. Not helpful. Not helpful because it's not telling me some stuff. $10mm. Let's see what this is. There's 20 pieces of it. See, that says resonant frequency 3 to 5. Material brass. See, that's just not gonna work. I just know it isn't. Twenty pieces, 25mm. I don't know. Let's try this and see what comes up. There's a hydrophone kit. Hydrophone kit. Well, I guess it's not going to show up here. Hydrophone leak detector. $250. This is not working out very well. I'm not buying shit off of eBay. I thought they had something here. Look at the exuberant prices on this stuff, see? If you could build something like this and sell it, you could make a killing. Dolphin ear hydrophones. Our newest 200 series. You get free software. Oh my god, there's that transducer. I'll bet you. Look how big that one is now. Are you kidding me? Look how cheap this is. How much are you selling this for? 7 hertz to 22 kilohertz. The DE200. My guess is this thing's probably at least a couple of $100, and these only got probably $50 wrapped up in this. Oh my God, look at this. Over $300 fucking dollars. And you get longer cables. That is ridiculous. By tuning in on a standard FM radio, because their FM sounds is what we was reading about. Oh my God, look at the price on this. Applications, research, education. What's this? I can't make this any bigger. It looks like that's the detector up top or something. Oh, there's a note here. What? The hydrophone disc was placed underneath the water reservoir to record the bubble stream as the pipe user inhaled. Oh, what? Oops, I didn't mean to read that there, but oh boy, yeah, I probably just wanted to make sure if he stopped inhaling or something, he might be, if he died or something like that. Oh my God. Let's see what the dolphin sound like. Well, I guess we're not gonna know, are we? See, these dolphin sounds go up to 150 kilohertz. And all he's got is just a transducer connected to the wire with a little amplifier. You gotta be fucking kidding me. These people are trying to make a killing on shit. See, at the center, there's an air cavity right here. And blue is the microphone. Oh, this looks pretty cool. How much is it, though? There's an operator's manual. A 150 to 20 kilohertz. It's not a good range. Let's add to cart. Oh, it's just gonna send me to PayPal. Holy fuck! Pardon my French, but look at this. Oh my freaking god. $1,300. That is fucking ridiculous. And this looks exactly like that one that was on YouTube that they were building. With that tube and the piezoelectric thing at the end, but they put it at the end and he put the epoxy down in the middle, and this one's built differently. Oh my god, that is ridiculous. That's ridiculous. Underwater drone for only 2,400. Yeah, baby. Underwater microphone currently unavailable. Of course it is. Epoxy. The piezoelectric cable. There's the thing right there. That's the kit that guy had. A honey tone. You got your honey tone me up. Boy, I wonder if the honey tone comes with the honey. I want the honey. The hell with the honey tone. I want the honey. See, it's at the end. Huh. I like that idea of using where that guy had the cylindrical, so you could get the range on the transducers. If you could just get the material. So it's been an interesting little night. It's only 1. Let's see, I don't know what the ranges are of this. I got a pizza stuff, but I'm wondering about this one's $69 from Kit Hub. That's the same one right there. $69. And you have to put it together with that freaking epoxy. Wow. I'm liking this idea. I'm liking this build. That was on YouTube. He had that on YouTube, but he put it on the end instead of, like, this one's different. They did something different. But this is only 150 to 20 kilohertz. Underwater hydrophone. See all buying options. $650. Wow. Um, $20 pieces. Gasket material. Buzzer, disk drive, piezoelectric. That's not ceramic. These are 35 millimeter. Those are 20 millimeter. They don't tell you. They don't tell you anything about frequency response, because they wouldn't, because they're not, people are not that bright on here. What if I typed in pizza material? Do you mean pizza material? Yeah, I probably should mean pizza material, you know? I really should. I'd probably get further in life. 6.3 kilohertz. Let's look for, let's see. $50 kilohertz piezo. 12.8, 50 watts. 10 pieces. 25 is 50 kilohertz. 30 to 50 kilohertz. Well, let's look up 10 to 100 kilohertz piezo. Multi-frequency. 28 kilohertz. 40, 100 kilohertz. What's this? See, these look like transmitter type shit. This is on eBay. $70. 62, 30 watt. Aluminum. Ceramic transducer. Comes from China. They build all the cheap shit. Look at this here, $20. eBay. They're probably all burnt out from boats and shit. Ultrasonic rangefinder. Frequency 100 kilohertz plus or minus 5%. This is just a 100 kilohertz unit. This is not a broadband unit. I should look up hydrophone, I guess. I like that idea where the guy was building the cylindrical stuff. Professional hydrophone. 10 hertz to 10 kilohertz. Hydrophone calibrator. 100 minus 173 dB. Of course, it doesn't give you a price, does it? Like, I want to buy this. Vintage hydrophone. $625. That's rather thin looking, isn't it? Looks like aluminum. Well, we're getting there, you know, I'm happy about what I've been looking at. I like this idea about that other thing he was building. This one's $200. That's still out of my price range. Ships from Hong Kong. Look how little that is. They are really upping the prices on these. I got all that freaking audio cable downstairs. RF spectrum analyzer. What is this? Is that software? What's this? Oh, that's only $72. That's a what is that? This is software. Allen no low noise mixing amp. Page 2. What the hell is page 1? RF spectrum. Yeah, I got a bunch of that stuff. What do we got here? It's an SDR. RTL SDR. I got 2 of those. Noise floor minus 60. That is horrible. I found out what that was. Is that SDR? What is this? That's an SDR. Wait, but this one's got a scope display. Ooh, I like the looks of this. That goes up to, well, that's 100 kilohertz to 1 gigahertz. That's cute. Everything is really getting small now. That's a nice piece of equipment. Tiny RF spectrum analyzer. I wonder if that's on Amazon. Well, we're not going to get into much on the old ghost hunting devices, but as far as that goes, it's a matter of noise. You know, we're building amplifiers that have low noise characteristics and that sort of thing. There it is, right there. There's the same thing for 40. I wonder if people know about this. That's 50 kilohertz. Too bad they didn't have a lower frequency. Oh, there's one right there. Oh my God, $50. That one goes down to 10 kilohertz. That's cool. There's another one. KK Moon. I think I'm gonna get one of these. That's an S parameter. That's for doing antenna shit though. SDR Geek, 100 kilohertz. Vector network, touchscreen, S parameters, blah blah blah, Smith chart, shit. It's not what I was looking for. Nope. Damn. The cheapest one they got is $75. And it only goes down to 100. That one's 70. There's one left. That's 100 kilohertz. Then we go down lower, kind of sucky. 50 kilohertz. I mean, you could build what's called like an up converter, you know, and it would work. 2.3 to 2.9 gigahertz. Well, that's a little bit limiting. Shit. That's just tempting, isn't it? Network analyzer. SDR Geek, $75. 100 kilohertz. But 100 kilohertz to 350? You can get the software probably. I mean, really, you just get the software. Is this eBay? Pizza material. Pizza contact microphone. Come on, eBay. Why the hell am I on eBay? $10 kilohertz. 20 kilohertz acoustic transducer for acoustic modem. It's just sitting there. I wonder what the hell my temperature is again. It's sitting at 60 degrees again because of everything I'm looking at. Our spectrum analyzer using a dongle. Yeah, I got that shit. Look where we started, you know? That'll give you a good description. Oh my god, look at this. Although most of the easily available piezoceramic discs will work, those extracted from greeting cards with diameter of around 28 millimeters are the best. The dimensions given presume this size. If using a ceramic salvage from the stores, carefully press off and discard the plastic cavity resonator that's clipped to the side. First, new ceramic discs, see note about soldering to ceramics. Take care not to overheat the ceramic, as the silver in the surface will dissolve, leaving a blackened, unusable zone. If you have access, set this to about 5 kilohertz, etc. You can sweep the generator to all rails, peaks, etc. To your underwater signals on headphones, you need at least 40 dB of gain and a preamp. I don't know what this polycarbonate is. 28mm. I actually have one of them cards. See, I don't know how much these are. One megahertz. I guess the only thing to do is really to grab the disc, or I gotta have a frequency response though. So if I use a tube and put them inside of a tube with say harmonic frequencies, let's see. He's using 303 and 344 meters per second.
Forms and surveys like this
Why did it
get
do this?
responses
You know, honestly. Fucking ads. Oh, what was that number? You know, damn it, he keeps scrolling up too damn fast. What the fuck, man? .495 hertz. So like if I wanted what if I could build a resonating chamber? Length equals 3. The wavelength is gonna be so it's 3 wavelength divided by 2, and the length is gonna be in meters. Must be closed tube and an open tube. And air. What if the tube is filled with water? velocity of the velocity would be quicker. If we used salt water, 32 degree Fahrenheit is probably approximately 4 times faster. The speed of sound in water is 3,000. So we've got to convert 3,170 miles per hour to meters per second. So 3170 okay, so 1417 acoustic resonance. End correction. Resonator. So L and frequency are reversed. Meters per second. Meters per second. Is that going to be in cycles per second? That's 0.0. If we want a resonant frequency of 12, wait, let's see. Dolphin frequency. So that's at 125 right there. Dolphin click frequency. That's their sonar. Let's try whale vocalizations are typically under 3 kilohertz. Damn. That's a big difference, see? Most of the gray whale's vocalization is below 1.5 kilohertz because they're bigger. They're bigger. So that's going to be 1 kilohertz, 10 kilohertz, and 100 kilohertz. So if I used wait, that's the length of a string. It makes a difference on the diameter of a pipe closed at one end. 1, 3. This type of tube produces only odd harmonics and has its fundamental frequency at an octave lower than that of an open cylinder. So if the diameter is large, wait, this is the formula here. So what's the wavelength of 1, 10, and 100 kilohertz? Oh, I didn't want to do that. Cones, closed rectangular box. V is the speed of sound, which is the speed of sound. That's going to be 3170. If this is in water, (3170) divided by the frequency is going to give me the wavelength, which will give me the length. Yeah, let's do this BS again. This is a constant thing I have to fight with. All right. So we've got 3170 divided by wait a minute. 3170 divided by the frequency. So it's 31. Uh-oh. Wait just a minute. Shit. I got so much shit here. I don't know what the hell that was. It's 1417 meters per second. So what we need is 1417 meters per second, and we're going to divide this by a frequency of 1 kilohertz. No. (10,000 hertz). That's going to give us our wavelength. Now, we're going to divide that by 4. And we are going to subtract 0.4 times the diameter will give us the length. If we subtract 0.4 times the diameter from that number in order to get whatever that length is, we're talking a very small acoustical aperture. What is this number? 1417 divided by 4. 1417, is it that's the wavelength in, oh, that's the wavelength in meters. So we can multiply this. 1 meter is actually 3 feet, I think. One meter is 3.3 feet. So we multiply this times 3.28. That gives us that in feet times a tenth of a foot is like 10 inches, or shit, 1 inch. A tenth of a foot is a little over an inch. This doesn't make any sense. I know it's small, but it doesn't make any sense because it just doesn't make any sense. I'm thinking in terms of putting water inside this sealed tube to create a resonant chamber so that the signal would be amplified before it goes to the amplifier, instead of just coming off that stupid whatchamacallit thing. But I got a feeling this only has to do with air. And I'm just thinking, well, why can't I make a tube with water? You know? Salt water. Who knows these things? Well, these guys are... Wait, what's this? These guys put out low frequency sounds. And the dolphins are at 125 kilohertz. Many recorded songs contained units that had high frequency harmonics extending beyond 15 kilohertz. A vertical array. Interesting. It's cool stuff. So I'm just thinking there's got to be 2 different transducers. One for low frequency and one for the higher frequencies. That's my thinking. 26. What? 1 micropascal RMS. 25 to 27 hertz. Doesn't really help me there. Minky Wheel. Minky Whale song. Of Iceland, near my neck of the woods. Oh. Huh. That might be loud. Yeah, okay. That took forever to load. Hydrophone array. There's this guy's thing here. How the heck does the sound go through this epoxy is what I want to know. Getting started with a fiber optic hydrophone, underwater microphone, marine acoustic transducers. Using a ceramic capacitor. Ooh, now what's this? Lo-fi do-it-yourself. Alright, let's check these ones out. Jab turkey. Whiteboard, basic hydrophone.
And frequency response. We'll begin by defining what we mean by hydrophone sensitivity.
Oh, God.
Acoustic signal. We'll now go on to consider frequency response. Other than the wavelength being measured, we can find As is also common with many needle hydrophones, there's a plateau region in the middle of the frequency response, in this case from about 15 to 32 megahertz. Hydrophone response is pretty linear. We have many cycles, all at the same sort of frequency as a function of frequency. It's also important to consider some of the sort of waveforms that we may be looking at. In this case, because of the high pressure levels, we also have nonlinear acoustic propagation, and this has led to harmonic generation. There's actually very small variation. This would be an appropriate choice of hydrophone for this application. We'll now consider the therapeutic signal. With the signals it's used to measure.
Yeah, what are they talking
Although
about?
sensitivity and frequency case we consider.
Let's get some good information there. Well, in the beginning. Let's see what else we got here.
Long time since I posted a video. Lately I've been working on ultrasound, and
This looks like my bench.
while I'm waiting for some real equipment to arrive, I decided to see if capacitors, off-the-shelf capacitors, would work as piezoelectric transducers. So this is a little experiment that I put together. and we have a 1 megahertz transducer down here and a little cup of water and some elastomer to couple into the water. We're driving that with a signal generator, just to generate a moderately strong ultrasound field, about 1 megahertz. It's actually a little bit less than that at the moment. Then at the tip, right there, we have a ceramic disc capacitor, and this is just a brass tube that I've got to kind of make something like a needle hydrophone.
This guy's crazier than me.
Capacitor. It's pretty old. I don't know the exact dielectric, but it's some kind of ceramic. And then up here we have a little buffer. There's a FET amplifier. It's set up for about 8 millisiemens transconductance, and then we have.
He's worse than I am.
Just a simple emitter follower after that to drive the coax, and that's driving back to my oscilloscope here.
Got nice scope.
In green is the transmit waveform. You can see the ring down of the transducers. So I'm using a signal generator just to produce a sinusoidal pulse. We send 5 cycles and then turn off. I guess you call it pink or red signal there is the trigger waveform coming out of the generator, and the yellow is the signal back from the hydrophone. You can see there's some latency, which is actual propagation delay, so it is actually an acoustic signal, not an electric signal. And if you move the transducer near the wiring for the transmit side, you can see the direct path just being picked up because the shielding isn't perfect. But yeah, so not surprising, I suppose, that piezoelectric materials that are used in moderate value capacitors are indeed piezoelectric and can be used for transducers. I mean, the transducer's nowhere near resonance. This is like one of the first capacitors that I found that actually does the job. That had any sensitivity, but this was essentially my just test setup. I just got a little cup of water, and then I could plop different capacitors in there when I soldered them to little bits of wire and had a look at them with the oscilloscope to see if they had any sensitivity.
Guy's pretty smart.
So I'm going to now hook this up to an XYZ scan platform and actually do some spatialized measurements of transducers using
Good
this.
lord. I'll skip that one. Spatialized measurements. To get that far.
Hi, Hart from Big Tree Media. That means I am stuck with figuring out how to either hold it in place or rig some fancy stand, rope, weird contraption. Tried mic stands and then tuck it under that first wrap, and that forms what's called a clove hitch. And now what this allows me to do is adjust the length simply by rolling and pulling this, and it will set how deep the hydrophone will hang, and it minimizes some handling noise by bunching up there on that noodle. And there you have it, noodle mount. Now let's talk about how not to get a good submersion. When I was the object already underwater, I was missing the transition I was looking for. My second method was to actually submerge the microphone with the object, so trying to bring as much air down with me as I could. I've found that many bubbles are the key to a good submersion. Another option would be to get an object that would hold some air in little pockets, like a plastic egg carton, that you could submerge under the mic. The key is to get a lot of air near or under the mic and let it out.
That's one way to test it, I suppose. Why don't these people talk in their displays? He's got a $1,000 tool to make a 10-cent device. That's a very thin tin can. What's he starting at right to? Nothing like the good old hot melt glue gun. He soldered something down in there. What did he solder in there? That's the piezo thing. That's a really dinky piezo element. He's working with the worst possible. Why in the hell has he got that bullshit fucking going through there? That's the worst possible wire you can work with. Okay, now what's he doing here? What is that rig? Not a clue. Clueless Harry here. No idea what that thing is. That's a pretty low frequency response. He's gonna shove it down his drain pipe. I wonder how the old sewer's working today. Oh. Yeah, but that's water. Okay, we don't want to hear water. We want to hear... That's just terrible, because how you want to hear... That's like a must be a low frequency spot. It's got to go through a filter to pick up the highs, you know? That's what I'm thinking. That's an interesting idea, though. And then he's got it in this big can. So I wonder if there's some resonance going on there that we don't know about. Build a... Tech microphone.
Want to build?
No, I don't want to build a membership site. I want to build a hydrophone. I've been sitting here for almost 4 hours trying to figure it out. No, that's this guy again. Yeah, I don't want to deal with this.
In a similar fashion.
This method.
Looking for feedback?
Not really, but. A piezo pickup instrument. Build a contact mic to make noise. What? Here's why S-traps are not allowed anymore. Sound design. What is this? Making a hydrophone. Reba, darling. Well, let's see what Reba's got in her little pipe.
So I'm gonna show you how to make an underwater microphone out of some stuff that you have in your audio kit and a little thing you audio cable.
Holy shit, that's expensive audio cable, girl.
The reason why is because as the contact microphone itself, you'll... So what we do, get up early, get shit done. So I've got a couple of contact microphones here. I'm only gonna make one. I have one that the cover keeps falling off. But I'm gonna leave this cover on, and I will tell you why. The reason why is because as the contact microphone itself, you'll get, you know, some good pickup in the water, but lack a tiny bit of resonance. And I'm hoping for just a smidgen of resonance. So I'm gonna leave this little cover on the okay? That coat we're gonna let dry. It would be an overlap like running down and like this.
Next.
Hey guys, welcome to Tech Time. This week I'm going to talk about using contact mics. Part in the middle of a session.
I have no idea what a contact mic is.
Company is the model P007. Comes with a little clippy. And
oh, look at the springs. Oh, he's made a reverb unit.
There's a lot of different kind of tonal possibilities. Now, you really get the benefit of this sort of shit when you have a lot of effects in your modular. If your modular is just a synth, this won't be very useful. Basically all you can do is filter. But if you have a bunch of effects, then you're good to go. So from the axis, I'm going to audio damage shapes, which is a distortion module, a wavetable lookup, algorithms, blah blah blah. And I'm using that to give it some gain and saturation. And then that's going to a spectre for FFT freeze, and then to a stereo reverb, and then out to the mixer. So.
That was rather interesting.
So, what's an S-trap and why are they prohibited? Whether it's an S-trap or P-trap, is meant to keep the sewer gases and other dangerous fumes of the city's sewage system from coming into your house, while allowing waste material to pass through. Each home produces waste, and this waste contains gases known as methane and ammonia, which are both toxic to the human body. Not only are these gases toxic, but they're also flammable, which means that if they were allowed into your house, they could cause some major havoc. Some cities had their sewer covers blown off hundreds of feet into the air, as rodents would chew on electrical wires and ignite these flammable gases. So
Holy
just imagine
fuck.
what it could do in your home. Every trap has a few different components. This is the sink or lavatory's tailpiece. This is the actual trap that would empty itself on the person drinking when greed would take over. The only reason why this trick glass would work is because there was no vent. If there was a small opening here, the pressure would equalize and the siphon wouldn't occur.
A little bit of a side journey. So this guy's making a contact mic. I guess it's electronics ASMR time today. God help me. He's obviously just making a cable. Oh, he's cooking. He's connecting the piezo cable thing to the audio. Just a direct connection. With no obvious frequency response or resonant characteristics. Jesus, what people do for fun. You know? Like me. Pizza Sound Sculpture. What's this?
You ask is
What was this metal thing that he put in the middle? Like, I'm confused. Like, what is this? It's not a magnet. And he puts the can on top. I don't know what that is. It's not explained in the video. Oh, maybe it is right here. A weight? It's just a weight. Why would you want to put a weight in there? I don't have a nice smooth ass can like that. That's what I need. So I guess there's some ideas happening. Live stream? What's this? Do-it-yourself hydrophone for $9. Let's see what this one is. Monterey Bay Aquarium. $11 and 12 minutes.
It's just a simple hydrophone. I've been making hydrophones for years. In fact, I make one that you can listen to stuff with it that I have online. I'll have some links down below. But this is one where you're going to be recording with it. You won't be able to listen directly. It's just going to be a jack you hook into an audio recorder. It's real cheap to make, and it'll go to 25 feet. I'll have links to the material used if you want to buy the cord or the microphones that I used, or you could see the videos that I've made before on how to make other hydrophones. But let's get started. You're going to be using a PVC cutter or a saw to cut your PVC, a hot glue gun, a piece of PVC about 3/4 inch length, and it's 1/2 inch PVC, 1/2 inch diameter, and a balloon that you can get at a dollar store, and a cable tie, some scissors, a piece of cardboard. Then you're going to need your actual microphone. And I purchased these. 6 of them, or 3 of them were for $6 on Amazon. They were really cheap, so they cost about $2 a piece. They're not very high quality, but if you just want to get started making and put the collar over the other end of your microphone, wind on it when it's underwater, I hope. And then next is the hard part of putting on the balloon. And once you're done with that, just put your cable tie on and you're all done. If you don't have enough ballast, it doesn't sink as well, you can put another weight on the outside. Wind on it when it's underwater, I hope. And then next is the hard part of putting on the balloon. And then let it set, let it harden, and then take off the foam protector that's used to keep the wind off your microphone. You won't be having much wind on it when it's underwater, I hope. And then next is the hard part of putting on the balloon. And once you're done with that, just put your cable tie on and you're all done. If you don't have a PVC cutter or a saw to cut your PVC, a hot glue gun, a piece of PVC.
I guess that was just a regular microphone.
Hello everybody, thanks for watching the video. This is the headphone that goes into the little microphone toy. We're going to be making it waterproof so you can put it underwater and make it into a hydrophone. It'd be handy for you to slide in your microphone. Also, if you buy large quantities of personal lubricant and happy birthday balloons, the retail clerks may get a false impression of you. So you make sure it'll sync on. Make money on eBay, and like I said, everything cut together.
What the heck?
And even drugstores, toy stores, for as little as $5-6. Well, with shipping might cost you more. Everything here I sell in the kit on eBay for about $10, but you can also get the items.
And this is the same one. I don't know what that shit is. Anyway, I think I got some ideas. I'm gonna save some links. And I still, well, we really need to figure out, like, we have to have a transmitter. I got a generator, but I have to have, so I'd have to make 2 of them probably. One for transmit and one for receive. I don't know. It's crazy. What time is it anyway? Probably time to go to bed. I mean, that idea, just hooking it to that piece of metal, you know, I don't, what's this? What the hell? Oh, this guy's pretty smart. Oh, he's gonna just melt it. Oh god, a new form of electronic ASMR. Jeez. I think this guy invented electronic ASMR. There's the pizza. Where's the pizza going? On the bottom of the thing. Or did he just glued everything to the pizza? That'd be a cool instrument. I'm a musician. It's like, oh my god, I got an idea for a musical instrument here. Oh shit. Huh. That's pretty cool. I got a kick out of that one. That's cool. I like that. Well, I'm gonna call it quits. I'm gonna save some web pages. I'd like to try that cylindrical freaking thing, but I can't get the. I'd probably just get rid of this wiki. Pizza. Definition of pizza. Pizza.com. What is this? That's a... Yeah. See these large ones? I mean, the different sizes, if you hook them up to something, they're going to give you a different frequency response. But then you've got to build a resonator. What if I looked up, this is kind of in line with my music, too. Underwater echo reduction. Underwater echo reduction minimized. Acoustic pressure. Oh, that's cool. They've got different designs in here to filter out for filtering. Like if you could make a filter, a Helmholtz resonator. If you could make a filter where the hell did that thing go to? Yeah, but that would, you could do it with a 3D printer, but then you'd have to have a way to tune the resonators. Echo reduction. Huh, isn't that cute, huh? Oh, they're putting, this is applied to a submarine to, huh. How'd they come up with that? Dimensions of the simulation model. Height, length, something. Medium water is used in this study. The length is in centimeters. Resonator unit cell. How would you move the structure? How would you change? How would you change that? Advanced marine innovation. Environmental monitoring. Wow, they're sending this stuff all to satellite. Energy harvesting underwater. Energy harvester. Polyurethane encasement, end cap washer, piezoelectric cylinder. That's what this other guy was talking about. Piezoelectric cylinder. What the hell do they make that out of? That's interesting. Yo. Ultrasonic removal of algae microorganisms. Oh boy. Let's just use this stuff to kill the ocean. Yo. How does a water jet work? Yeah, I want to build one of those too. What is this? What is this? Helmholtz or acoustic resonator. Yeah. Acoustics.org. Lots of stuff. Lots of stuff. What's this? Topological phononic states of underwater sound. Huh. Based on coupled ring resonators. Well, that's really not going to help me out, is it? Sacred underwater basin, I would have to click that. Huh. Cute, huh? Real cute. I wonder what this stuff is made out of. Standing waves in a pipe. This looks like my... What is this? Standing waves in pipes. Sensors. Piezoelectric electrodes. So if I took the piezoelectric thing and wrapped it around material, novel acoustic filtering. I don't know what that is. I think it just boils back to this little idea. The Helmholtz, I wonder if I could type that in here. Helmholtz underwater, Helmholtz resonator transducers. I wonder if that's on YouTube. When was this? 1977. Elastic wall fluid cavity. What is this interesting stuff? Equivalent circuit. Someone Japanese. Yeah, you could have, well, let's see, you could have an electrically driven element like when you do microwaves. You could have an element inside there that moves around. To somehow change the resonant frequency inside the tube. How would one do that? Alright, this has got to be it here. What time is it? Getting freaking late.
The volume right here is from the level of the liquid to the neck, and the neck, the size of the neck as well. Helmholtz resonator. Helmholtz. You would have. I guess I can erase tyranny, right? I'm Helmholtz now. You would have. Okay. So can you all see the flame? Yes. Okay. Now I'm going to turn this cavity So what's that? Resonance. Okay. So I'm going to just increase the sound level. So I'm essentially making these oscillations very large, and so it pushes even more air. Right at the neck of the Helmholtz resonator. Now, when you have fluid in motion, there is a reduction of the pressure. So in a Helmholtz resonator, you would have, I guess I can erase tyranny, right? I'm Helmholtz now. That effect. I'm going to show you that effect with this candle, not the paper, with this candle right here.
which is the mass on the spring. This mass will be pushed in air. This is speaker, 510 milliliters bottles. This one is random function generator, which will generate the sound wave with the frequency that I want. And an amplifier, which will give enough power to make loud sound. Before I start the experiment, I measured the natural frequency of the bottle by using the spectrometer analyzer. The natural frequency of a 510 milliliters bottle was 200 Hz. Now I make the random function generator to generate sound wave with 200 Hz and see what happens to the bottles. And the bottles move. But why this is happening? Before the speaker makes sound, the pressure inside and outside of the bottle are the same. Both have atmospheric pressure. The air jet from the speaker will move the air outside the bottle. According to Bernoulli's principle, as the speed of the fluid increases, the pressure within the fluid decreases. Now the air pressure outside the bottle becomes lower than the atmospheric pressure of the air inside of the bottle. The pressure difference makes the air inside the bottle to flow out. As the air rushes out, the bottle moves in the opposite way to compensate the effect from the airflow. In this transient state, the bottle moves to conserve the momentum. The air flows out until it reaches to the steady state, where the pressure is not strong enough to overcome the resistance, such as air resistance. If we remove any resistance or if we produce a sound strong enough to overcome resistance, we will be able to observe bottles rotating continuously after the kick. The more interesting thing is, if you try this with a frequency that is higher or lower than the natural frequency, you will observe that the bottles do not move. I can explain this with the quality factor of the bottle. The highest frequency that still moves the bottle was 217 Hz. Then delta omega over 2 is approximately 2 pi times 17. Therefore, delta omega is about 213. Quality factor of the bottle is omega over delta omega, so its value is roughly 5.89. So the bottle's quality factor is quite big, which means that the resonance curve is really sharp. As you can see from the sharp resonance curve, any frequency higher or lower than the resonance frequency will have negligible effect on the oscillation of the air inside the bottle.
Okay. I'm gonna call it quits. I got some ideas. I gotta figure out something.